G'day viewers, my name is Rick Stawdy and many thanks for investing the time to participate in this presentation, The History of the Cosmos. What are we going to cover? The first thing we're going to look at are the present epoch cosmological characteristics and parameters. We'll present a CMBR constrained solution and a CMBR unconstrained solution. The unconstrained solution is well known. We call it the standard model of cosmology. The next section is termed the big picture, and similarly we're going to present a CMBR constrained solution and a CMBR unconstrained solution spanning the entire history of the cosmos this time, not just the present epoch. In section 3 we're going to take a very close look at the evolution of the primordial universe. In section 4 we're going to walk you through what we call the cosmic envelope and show you how cosmological inflation envelops multiple events, including cosmological acceleration. In section 5 we're going to show you how 3 authoritative estimates relating to the commencement of cosmological acceleration are in fact in conflict with each other, hence the cosmic acceleration problem. In section 6 we'll move on to the flatness problem. We're going to suggest that the geometry of cosmological spacetime is in fact barely open, hence appearing as flat to our technology. And in section 7 we'll conclude with a presentation closeout, and if we have time we'll have a look at the appendices. So let's begin with a brief overview of the present epoch. What you're seeing now is a comparative overview of key present epoch cosmological metrics. As you can see quite clearly, even at a quick glance, the correlation between solutions is astonishing, with one noticeable exception: cosmological age. Many of these results were published in the Hindawi journal, Advances in Astronomy, in 2020, a couple of years ahead of the James Webb Space Telescope. I should also point out that our solution improves approximately 23% of the particle data group 2022 astrophysical constants reference table. Appearing in the left-hand column, we see the CMBR constrained solution and the standard model of cosmology solution in the right-hand column, which is CMBR unconstrained. What you're probably all asking yourselves now is, what is EGM? Never heard of it. Well, EGM is a method, not a theory. I must stress this again. It's a method, not a theory, and is not in competition with general relativity or quantum mechanics. However, it does use elements of both disciplines. Now, I'm an engineer, so I solve problems utilising well-established engineering tools. Physicists use the tools they know. Engineers are no different. Engineering is pretty much specialised physics. We don't study the breadth of science that physicists do, but we study certain specialisations of science at a significantly greater depth than physicists do. One of the specialisations we do know a little deeper than physicists is thermodynamics. So what you're seeing now in the left-hand column is basically a thermodynamic solution. All derivations, proofs and applications of the EGM construct are freely available online, or you can reach out to me directly and I'll be happy to help. Let's now take a look at the big picture. This is a 2008 illustration of cosmological history. I've had to make a number of changes to bring it up to date, but nothing too radical. I've emphasised the key differences between the standard model of cosmology version of cosmological history, which is not constrained by the CMBR, and the EGM version, which is constrained by the CMBR, on the next slide. We'll get to the EGM version shortly, but for the moment I'd like to draw your attention to the circled question marks. This basically means that, as far as the SMOC is concerned, cosmological inflation started at some time before the Big Bang and not at a logical origin, that is, not when t equals 0. This is not a terribly important point, but I wanted to put it on the table. The period of cosmological inflation is a significant area of mystery for the SMOC. The old narrative depicts the Big Bang followed by cosmological inflation. Nowadays, the reverse is realised, whereby the Big Bang is shown to occur at the end of cosmological inflation, as stated by Siegel. This logic means that if cosmological inflation finished at approximately 10 to the minus 35 seconds, that's when the Big Bang happened. This doesn't seem quite plausible to me, and I'm not convinced. Another key area of dispute for me is cosmological age. The SMOC age of 13.8 billion years is the iceberg that sunk the Titanic. James Webb Space Telescope observations of galactic structures containing billions of stars being formed within 2 to 300 million years after the Big Bang are too impossible to believe. Moreover, recent James Webb Space Telescope claims of galactic mergers being observed dating back to 400 million years after the Big Bang are completely ridiculous. It's just not enough time for all this to have happened. We seem to forget as a community that cosmological age is a calculation, not a measurement. EGM insists that the SMOC calculation of cosmological age is incorrect, and I'm completely certain that in the fullness of time, the James Webb Space Telescope or equivalent apparatus will experimentally confirm our calculation of 14.6 billion years. Let's now take a look at the CMBR constrained solution for the history of the cosmos. This is the EGM solution for the history of the cosmos. This is what the standard model of cosmology looks like when it has been constrained by the CMBR. To add a bit more flesh to our description of the EGM construct from earlier on, it's fair to say that the EGM construct bridges electromagnetics, general relativity and quantum mechanics. This is not the same thing as unifying them. It bridges them, it links them together, it doesn't unify them. The EGM construct is not a grand unified theory of anything, it's a method of solution. So at the end of the day, what we get out of this is a quantized representation of gravitational acceleration, which is equivalent to general relativity. From this GR equivalence, we obtain what you're seeing now. We obtain the CMBR constrained version of the standard model of cosmology. Now, having said all this, the key differences between this slide and the previous slide is that we show cosmological inflation to be a period enveloping the Big Bang and very, very importantly, cosmological acceleration. I'll circle back to cosmic acceleration a bit later on, but for now we'll focus on the fact that this CMBR constrained solution estimates the James Webb Space Telescope galactic structures to be 1.3 billion years old, not 2 to 300 million years. Instantly, this leaps out as being a far more realistic and plausible reality. It would also mean that the apparent observations of galactic mergers actually occurred at approximately 1.5 billion years after the Big Bang, not 400 million years. Once again, our result appeals to common sense. Now, when I was a young engineer, just starting out my career many years ago, a very experienced and seasoned design engineer said to me, "If the solution looks wrong, it is wrong." I've never forgotten that life lesson, and I apply it to the SMOC calculation of cosmological age and James Webb Space Telescope galactic formation and mergers. Let's now take a look at the cosmological constant. The cosmological constant was flippantly invented by Einstein to accommodate his conception of a static universe and therefore is actually constant. It does not vary with time by definition. However, nothing was known about an accelerating universe in Einstein's day, so including a constant seemed to make sense. The trouble is that nature tends to be nonlinear. This slide exhibits the EGM solution for the cosmological constant, constrained by the CMBR. It should not escape your attention that it changes with time. It is definitely not a true constant. However, no truly constant solution can exist due to the influence of cosmological acceleration. Our solution was forwardly derived from first principles, and all the equations and information required to replicate these curves appear on the illustration. This image contains two graphs. The first graph plots the value of the cosmological constant in the primordial universe, whilst the second graph plots the late age value of the cosmological constant. There are 5 important instances on these graphs. The first is the Big Bang at T alpha. The second is when the cosmological constant transitioned from positive to negative at root 2 T alpha. The third significant instance occurs when the cosmological constant transitions from negative to positive at a cosmological age of 7.3 billion years. The fourth significant instance occurs when the cosmological constant reaches its maximal value at a cosmological age of approximately 11 billion years. And the final significant instance occurs in the present epoch. The most important observation to make with this illustration is that the cosmological constant was negative for the first half-life of the universe. However, it is now positive and shall remain that way. Let's now take a much closer look at the primordial universe. Here we have the cosmological history of the Hubble constant in the primordial universe. I realise that this illustration appears baroque, but once you get your head around some basics, it's not too difficult to follow. This illustration contains 3 graphs. It is important to note that all required equations appear on the illustration, so everything you need to replicate this solution is right in front of you. Everything you see here has been forwardly derived from first principles, and nothing has been doctored, modified or fine-tuned. The first graph is the magnitude of the Hubble constant. The second graph is dh to t, which is the rate of change of the Hubble constant in the time domain. The third graph depicts cosmological inflation and expansion. The next important feature to recognise is that each graph contains regions. Each region defines a specific phase of the evolutionary process. Region A denotes the period we term Planck inflation. This runs from t equals 0 to t alpha, which is the instant of the Big Bang. I'll also point out that the CMBR at that time was 0 Kelvin at the instant of the Big Bang. So the Big Bang was in fact cold, but thermally inflated extremely quickly. Region B denotes the period we term thermal inflation. This runs from T alpha to T1. At T1, the CMBR reached its maximum value, which was approximately 10 to the 31 Kelvin. Region C denotes the period we term Hubble inflation. This runs from T1 to T2. From the graph you can see that the Hubble constant reduced to 0 by T1 for an instant, but immediately shot upwards again to its maximum post T1 value at T2. Its value at T2 was approximately 10 to the 60 kilometers per second per megaparsec. Region D denotes the period we term Hubble expansion. This runs from T2 to the present epoch. Region E denotes the period of cosmological inflation from t equals 0 to 2t phi rho. So cosmological inflation ended when the universe was approximately 10 to the minus 23 seconds old. Region F denotes the broader period of cosmological expansion from the Big Bang at T alpha to the present epoch. An important takeaway from this illustration is that cosmological inflation was a multi-event, multi-process period. This is why we term it as being the cosmic envelope. Let's now look at the behaviour of the CMBR. Here we have the cosmological history of the CMBR in the primordial universe. You will instantly recognise the black body radiation curve similarity. This was not intentional. Black body equations were never utilised in its derivation, but the fact that its shape mimics a black body curve is very comforting. The illustration contains 4 graphs. The first graph is the CMBR in the time domain. Note that the temperature of the universe at the instant of the Big Bang was 0 Kelvin, so the Big Bang was cold. The cold Big Bang model was abandoned by physicists after WMAP and Planck satellites observed the CMBR which we see today. However, in our solution, the cold Big Bang hides behind a hot Big Bang observation. In other words, the universe was 0 Kelvin at the instant of the Big Bang, but rose to 10 to the 31 Kelvin within the first 10 to the minus 42 seconds. So in fact, the WMAP and Planck satellites are blind to cold Big Bang evidence. Hence, cold Big Bang models cannot be excluded from the standard model of cosmology. This is an important takeaway. The other graphs are the first time derivative, the second time derivative, and the third time derivative. Let's now move on to a detailed inspection of cosmological inflation and accelerated cosmological expansion. This is an illustration of cosmological history which involves a detailed account of the cosmological inflation period. We'll deep dive into this illustration momentarily, but we can summarise the history of the cosmos from the Big Bang to the present epoch by outlining 14 key events. The 14th event is a general reference to the distant future, and the 13th event refers to the present epoch. So between the Big Bang and now, we've identified 12 key cosmological events. To begin with, we identify the start and end of the cosmological inflation period. You can see that cosmological inflation started at t equals 0 and finished by 2t phi rho, that is, when the universe was about 10 to the minus 23 seconds old. Our estimate is slightly longer than the standard model of cosmology, which estimates the cosmological inflationary period to have finished by approximately 10 to the minus 35 seconds. Let's now walk through the illustration. The first key event was the Big Bang, and it occurred at T alpha. At this instant, the cosmological temperature was 0 Kelvin, and the magnitude of the Hubble constant was approximately 10 to the 61 kilometers per second per megaparsec. The second key event occurred at root 2 T alpha. This is when the cosmological constant transitioned from being positive to negative. At this instant, the cosmological constant and the dark energy density parameter equaled 0. The third key event was the instant when cosmological acceleration began, represented by T1. At this instant, the CMBR was at its maximum value of 10 to the 31 Kelvin. The Hubble constant decreased from its Big Bang magnitude of 10 to the 61 kilometers per second per megaparsec to 0, but only for an instant. The instant when the Hubble constant was 0 is the instant when cosmological acceleration began. By the time the universe was 10 to the minus 42 seconds old at T2, the Hubble constant had increased from 0 to approximately 10 to the 60 kilometers per second per megaparsec. So this means that for an instant in time, the universe stopped expanding, then started expanding again. Although it had stopped expanding, it was continuing to inflate, and that's very, very important to retain that. It continued to inflate. Now, an analogy to the behaviour of the Hubble constant I've just described might be a ball thrown into the air. At the top of its travel, the ball's velocity is 0, but it continues to experience constant acceleration. Therefore, the velocity of the ball is analogous to the Hubble constant, and our constant gravitational environment is analogous to the cosmological inflation environment. Now that we've looked at cosmological inflation in some detail, we're going to scrutinise the 8th, 9th and 10th events. These events relate to the standard model of cosmology estimates for the commencement of cosmological acceleration. Now, to cut a long story short, the standard model of cosmology is in conflict with itself, and from this we've identified what we have termed to be the cosmic acceleration problem. Let's now do a deep dive into it. In this illustration, we see the dark energy density parameter plotted by the red curve, the pressureless matter parameter plotted by the blue curve, and the deceleration parameter plotted by the magenta curve. The PDG estimate for the commencement of cosmological acceleration is represented by the red circle. The US Department of Energy estimate is represented by the black circle, and the Fermilab estimate is represented by the magenta circle. Let's now scrutinise the cosmological acceleration problem. We saw on an earlier slide that the 8th, 9th and 10th cosmological events were the basis of a standard model of cosmology issue termed the cosmic acceleration problem. The particle data group assert that cosmological acceleration commenced at approximately 7.7 billion years. However, the US Department of Energy assert that the actual figure is approximately 9 billion years, and Fermilab assert a value of approximately 10 billion years. So these three authoritative references disagree with each other. The reason this conflict has occurred is because none of these standard model of cosmology solutions are constrained by the CMBR. The evidence for this is displayed by the calculated values of cosmological temperature. All three events are attached to distinctly different thermal conditions, so it appears that these distinguished institutions have observed cosmological evidence of something, but may have misinterpreted their results. We'll come back to that in a moment, but for now let's inspect the EGM solution. First off, the EGM solution is constrained to the CMBR. Second, It commenced during the cosmological inflation period. This makes much more sense than the standard model of cosmology claim that all points in cosmological 4D spacetime suddenly decided to get some exercise and run away from each other by accelerating their expansion for no apparent reason. Clearly, the SMOC solution for accelerated cosmological expansion belongs on a theatrical stage as a supporting act for David Copperfield. It's magic, not science. The EGM construct has analysed these SMOC results and determined that the particle data group conclusion actually relates to the instant when the cosmological constant and the dark energy density parameter equaled 0. In contrast, the US Department of Energy solution actually relates to the cosmological instant when the dark energy density parameter equaled the deceleration parameter. However, the 2008 Fermilab solution correctly identifies when the deceleration parameter equaled 0, that is, the instant when it transitioned from being positive to negative. Let's now inspect the EGM solution in detail. This is what the standard model of cosmology would look like if it were CMBR constrained. This is a graph of dH to t, that is, the rate of change of the Hubble constant in the time domain. You can see in region B that the Hubble gradient is negative from the instant of the Big Bang at T alpha to the instant of maximum cosmological temperature at T1. This region of negative Hubble gradient means that the universe was decelerating between T alpha and T1. However, at precisely T1, it stopped decelerating and started accelerating. The instant of maximal Hubble constant is marked by T2. This instant coincides with the instant of maximum cosmological acceleration. So, the expansion of the universe started accelerating at T1 with its peak value of acceleration at T2. From T2 to the present epoch, the universe continues to accelerate, but it is accelerating at a slower rate now than it did at T2. So you can think of it like this. The universe is currently accelerating, but the rate of acceleration is decreasing asymptotically to 0. This means that the universe will achieve a constant speed of expansion after an infinite amount of time when the acceleration reaches 0. One of the most significant messages to receive from this slide is that cosmological acceleration was derived organically within the EGM construct and did not require any band-aid fixes or inclusions. By following the EGM method of solution, the standard model of cosmology is not required to execute any adjustments in order to accommodate observational data. Next, we'll investigate the flatness problem. Three possibilities exist for the space-time geometry of the universe: flat, closed, and open, as depicted in this illustration. Presently, the standard model of cosmology asserts, via physical observation, that the geometry of the universe is flat. At least, that's what our present level of technology measures. However, this gives birth to what's known as the flatness problem. The flatness problem is the astonishingly remarkable coincidence that the universe contains just enough mass to halt its expansion and achieve Einstein's preconception of a static universe, but only after an infinite period of time. This also means that no matter how flat our technology measures the universe to be today, it must have been even flatter at the instant of the Big Bang. So this flat conclusion is what science gets via a CMBR unconstrained cosmological model. However, when we constrain the standard model of cosmology to the CMBR, we achieve this result. So, the EGM position is that the universe is presently barely open, but on its way to becoming asymptotically open in the far distant future. Therefore, the flatness problem does not exist. Let's close out this presentation and summarise what we have covered so far. We've covered quite a bit of material in the presentation. Too much to repeat here, so we'll stick to the essential messages. Firstly, we have demonstrated the benefits of weaving the standard model of cosmology together by constraining it to the cosmic microwave background. The reason this technique is so effective is because the CMBR is the most accurate cosmological measurement which presently exists, and will remain so for many decades. In its current form, the standard model of cosmology is more anchored to the Hubble constant than the CMBR, and therein lies its weakness. However, However, the EGM construct has formulated a relationship between the Hubble constant and CMBR, and this is the reason why we are able to achieve such astonishing results. In addition, we showed that the period of cosmological inflation encapsulated multiple events. Next, we identified and resolved the cosmological acceleration problem, and lastly, we ascertained that the flatness problem does not exist. It merely appears to exist due to our current level of technology. Let's now take a look at the governing equations. These are the governing equations relevant to this presentation and our research article. Of these very simple 6 equations, the most important one is equation 5, as emphasised. Generally speaking, physicists do not value or trust equations when they themselves have not understood or are aware of the derivation process. In this case, these equations are so simple that the results speak for themselves. However, if you would like to understand how these equations have been derived, you can read about it, or you can take the easy path and reach out to me for guidance. I'll be happy to help. Let's now take a look at the supporting equations. The supporting equations are 2 simple groups of mathematical and physical constants. They have all been forwardly derived from first principles and denote exact solutions. Well, viewers, thanks for watching this presentation. I hope you found it interesting. If you would like more information, please refer to the links on the screen or reach out to me via email. It's been a pleasure, and I hope to present to you again soon. Cheers.